So IMFs are all about physical properties or the attractions between particles, not the bonds within those molecules. And one of the ways that we can attract particles or have a physical change is to mix things together. So when we make an element and turn it into a compound or a compound into another compound, we make some bonds, we break some bonds, that's a chemical change. But when I take things and put them together physically, either in a homogeneous or heterogeneous mixture, then I have undergone a change that involves breaking and making IMFs. A lot of the times we think of solutions as just liquids, but it really could be a solid, liquid, or gas solution. And all of those are governed by the strength and types of IMFs. Within our solution, we have the different parts. We've got the thing that gets dissolved, our solvent, our solute, excuse me, and we may have more than one solute, and then what it gets dissolved in, which is our solvent. Most of the time we kind of picture and use water as our solvent, and when that happens, we have aqueous solutions, but it's possible to have solutions of all different types, non-polar solvents, gaseous solvents. We're just mixing things that are different in terms of their attractions and properties. So one of the things you'll see a lot with solutions is a particulate diagram. So that helps us to tell the difference between things that are chemically bonded versus things that are physically mixed. It also kind of helps us recognize the difference between an even distribution in a homogeneous mixture, like a solution, or that uneven distribution, maybe with clumps or visible differences. Sometimes it's very obvious when you look at a heterogeneous mixture that it is heterogeneous. When you put sand in water, the sand settles right down to the bottom right away. Other times it's not as obvious, where you can't see the separate components. There's different ways that we can look at that or be able to tell that. Sometimes the ability to filter, sometimes it'll stand. One thing is the Tyndall effect, which is when you have a light source like a flashlight, headlights on your car, or a laser beam, when it goes just through the air or through water, you wouldn't be able to see it. But when you have smoke, when you have fog, when you are a spy and you blow dust into the air to see your laser beams, that is creating a colloid or suspension, and we're able to see the beams. When we look at that, that is one way of telling us what's mixed. But really, we want to focus on the attractions that are allowing it to mix. What sort of attractions are holding the solution together? And are there any repulsions or attractions that would make it come apart? One thing that helps solutions become solutions is the thermodynamic concept of entropy. So entropy, and we talk about this with thermochem, with thermodynamics, it is a measure of the randomness or disorder in a sample. And one of the things that we know in terms of laws of thermodynamics in the universe is that the universe tends towards greater entropy or the dispersion of energy. So there's lots of different definitions of entropy, but in terms of solutions, it's kind of like that mixed up combination of things where the more mixed up or the more random it is, the more entropy that we have. So if I take two pure substances and they're in separate containers, obviously they aren't mixed. But as soon as I put them together, those particles are moving randomly if it's a liquid or gas. Even as a solid, they're vibrating. If I get them moving fast enough, they are going to be interacting with one another, and they are going to move randomly unless there's something that's keeping that from happening. So entropy kind of drives all mixtures, or makes it more likely that things would be mixing. But when we're thinking about this, the entropy or the randomness is helping, but also the IMFs. When we go from reactants to products in a chemical change, we break bonds, we make bonds. When we go from solute and solvent to solution, we break IMFs and we make IMFs. In that case, we put some energy in order to break the IMFs. So right here, if I had something like sugar, to get those sugar molecules separated, I would have to put in energy. To get water, if we're dissolving it in water, to get those water molecules farther apart so that there's space, I'd have to put in energy. I'm breaking hydrogen bonds in both cases, dipole attractions and dispersion forces. When they come together, though, we make an attraction between them. there is, in this case, a dipole to dipole, some hydrogen bonding, and some dispersion forces if this was sugar and water. And no matter what things we're mixing, there is some sort of attraction, be it ion to dipole, be it dipole to dipole, dipole to induced dipole, dispersion forces. So we are always breaking attractions, and then there's some sort of attraction that's being made if we make a solution. When the making or the release of energy is a larger amount of energy than the energy we have to put in, it's definitely favored from the standpoint of energy or enthalpy, or in terms of maybe a heat or temperature change. So we've got entropy helping us out, and depending on the IMFs we're breaking and making, we may also have energy or enthalpy helping us. And here are some more specific examples, because this is a little bit tricky kind of visualizing this abstractly. But as I look at specific examples here, hopefully we can think about, well, what is the IMF and why is that good? So right here, I have Na to Cl to Na to Cl. That is an ionic bond or an ion to ion attraction. That's very strong. Here I have water. Water strongly attracts other water molecules with a dipole and hydrogen bonding in addition to the dispersion forces. And when we come over here, we make an ion to dipole attraction. The ion to dipole attraction is greater than the dipole to dipole or the hydrogen bond. And because I'm able to make so many ion dipole attractions, the 4 here and the 4 here don't really do justice to how many, when we look at this three-dimensionally, how many water molecules could surround a cation or an anion. Each one has a specific number, but it's often a number that's more than 5, sometimes more than 10, making lots of ion to dipole attractions. So here, the total energy released by those ion dipole attractions is likely to be larger than what need to be broken to break these apart and to break the water apart. When that happens, our solution definitely will form. It will dissolve. Salt water is a good example of that. So here I've kind of made a table. When this happens, when these attractions are greater than these attractions, or this attraction to itself and this attraction to itself, my solution will form, and salt water is a great example. The second one is alcohol and water, or ethanol and water. Ethanol is polar. Ethanol has O to H bonds, or it has hydrogen bonding to itself, but also hydrogen bonding in between. When I put those two together, initially they stay apart, but then they do mix together because of the attractions that we can make. The attractions between ethanol and water are dispersion forces, dipole-dipole attractions, and hydrogen bonding. The attractions that we're breaking between ethanol and ethanol are those exact same 3. The attractions that I'm breaking between water and water are those exact same 3. So here I'm breaking dispersion, dipole, and hydrogen. I'm making dispersion, dipole, and hydrogen, and they're probably pretty similar in strength. The solution will form in that case because the energy in and the energy out is about the same, and the entropy or randomness helps it to kind of drive or to mix it up even better. Alcohol and water is a great example of that. Oil and water, or this is really hexane and water, do not mix. So here, the attractions between them, and sometimes we say there's no attractions between them. Here's some description, but there is an attraction. Water induces a dipole onto that hexane, or it would also work the same with oil. So there's an induced dipole to dipole attraction. There is some attraction there. If we mix them up randomly, we would have greater entropy. So those things are favorable, but those attractions that I'm making are much weaker than the hydrogen bonds between my water molecules. The dipole to dipole and hydrogen bonding within water is stronger than the attractions that we make. It's not that we don't make these attractions. And another important piece of that is right here we have only London dispersion, or only induced dipoles. The induced dipole to dipole between the oil's attraction to water is probably a little bit greater than oil's attraction to other oil. The problem here is that the water sticks to itself very well. the water attracts other water so strongly that it pushes the hexane, the oil, the nonpolar thing out. So when we're looking at these, it's very important to think about the attractions that we're breaking and the attractions that we're making, often listing all of those and then comparing which ones are stronger. Data or the presence of a solution or lack of a solution is great data to help us quantify or predict that as well, just like with other IMFs, understanding how we can describe the properties.